Who we are? Basically, we are a company that was founded, almost 20 years ago now, with one mission, which is bring trust, transparency, and technology to the music industry. And technology is the key here because, quite often you will find that this is not really the case in the music industry, especially around labels. So where do we fit? You can see basically there's a consumer layer, which is basically who listens to music, and there's a retail layer like Spotify and whatnot. And these things are growing and growing every single day. Then there's a society layer, which is basically who handle things in the different territories. So in the UK, you have PRS, in Italy, we have CIA. So there's all sorts of society that actually collect the royalties to give them to the artists. And then you have a level that is basically where Cobalt fits, which is a publisher or a record label, and basically they help the creators to get the money they need to get from the different territories. When I talk about this, basically what I'm talking about is like publishing, recording, neighboring, and a lot of things like that. You can think of it as like, there's who wrote a song and needs to be paid, there's who sang a song, who played an instrument in a record, the band's manager, the ex-partner of a band member or something like it that got a divorce settlement, whatnot. And so all these people have different kind of deals, and basically we need to make sure everyone gets their share of money. This doesn't really look, kind of see something underneath, but basically what I'm trying to point at is basically, this is pretty much what we do. Cobalt is here in the middle, and basically you have a perspective of, okay, someone creates a song, and then we need to make sure that everyone is aware of who manages that song, and then on the other side, basically the money flow of a song that was played, and basically royalty money that comes back. And you have to think that basically the music industry has been dominated for a long time by some very big labels that basically have been around since forever, and basically decided that the technology they used to have at that time is still fair enough. But obviously, with the exploding number of things over here, when we try to deal with big numbers, but then we use CSVs or PDFs or fixed with text files or all sorts of very static old word kind of thing, things are harder. So what we try to do here at Cobalt is really bring in the technology element that helps dealing with billions of royalties. You have to think that before you were buying a CD once, and so royalties were just coming back once. Now you're listening to a song through Spotify multiple times, or to YouTube or whatever. So every single time there's a new line that comes down. So the data is exploding here, and we need to do something about it. And that's really what Cobalt tries to do, is try to help people getting their money and simplify the whole technology layer above. To give a bit of context of really who we are dealing with, we might, not a lot of people really heard about Cobalt, but actually if we look at, who we signed, for example, there's actually a lot of, big artists and big players. And if we look at the top 6 publishers, you can see how we have the big labels that everyone kind of knows, Sony, Universal, Warner, and Cobalt is just there. So we actually had a lot of buy-in in what we are doing. We started relatively, recently, 2000, but still we are now a big player in the industry. And why is that? Well, it all goes down to the mission that I was explaining before. So this is basically our CEO, and basically what he's trying to tell is like, we want to eliminate pain points for creators. We want to make these words simpler, faster. We want to make these words somewhere there, it's fair for the creator, and at the same time, it's as fast as we can.
Okay, cool. So the title of my talk is Thinking Like a Data Engineer. I'm Ben Parker. I'm the Senior Data Engineer on the same team as Luca, and proud owner of the second best beard in the team. My talk today is going to be about my transition from back-end engineering to data engineering. So 2 years ago, I worked for ITV as a back-end engineer focused in Scala. And after that, I moved to The Guardian, and now I'm here at Cobalt doing a very data engineering focused role. Now, for me to really talk about the differences between those two worlds and what the transformation between the two is like, I kind of need to talk about what a data engineer actually is. I tried Googling this just to try and find an actual definition of data engineering versus back-end engineering, and I couldn't find a definitive one that everyone agreed on. So I'm going to give you mine, and maybe we can talk about it afterwards whether you agree. So to give my example, I'm going to talk about an arbitrary company, which isn't actually Cobalt, but is what a kind of tech department generally tends to look like. We start with some users who talk to a front end. For my example, you have a front end in which users can go through a few pages, they log in, once they've logged in, they pay for things, and that's the general structure of the website. Now, to handle these different separate entities within the company, you will traditionally build a collection of back-end services. Each of these services handles a single responsibility within the company, and they will have their own data store. There's no reason why these data stores will be the same as each other, or even using the same technology, or in any way kind of communicable between each other. And that's a good thing. The engineers in charge of that advocate this, because it means that they can work independently and choose their own technology. However, at this point, someone from the business comes along and asks, okay, of the age 25 to 35-year-old people who visited our site, what page did they visit before they bought our products? And you go, but those are 3 different systems. We don't really have a plan for that. And that is where data engineering tends to enter the picture. Now, a rather standard way of dealing with this that I've experienced, although there are quite a lot of different architectures which satisfy the same problem, is that you have a data engineer who handles the kind of disorganized data that comes off the back of these systems, and they will organize it in some fashion, and ideally present it back to the people in the company who want to ask these questions. Now, some various methods, you might, for example, have the organized data queryable by something like Athena or Presto, so that when users want to ask questions, they can do whatever they want. You've organized the data so that it's easy for them to use. A crucial point that I found when transitioning from the kind of back-end engineering section to the data engineering section is that there's a kind of difference in orthogonality within this picture. A data engineer tends to think horizontally. They think about the breadth of the company. They may be talking to 10, 15 different teams within the company, whereas a back-end engineer tends to be focused within their single responsibility. And so to transition from one to the other, I found I had to lose a little bit of knowledge depth in favor of breadth. So I'll understand a little bit about as much of the company as I can so that I can handle their data, as opposed to a very in-depth knowledge of a very specific part of the company, which is quite a strange transition, and it's kind of my first real point of what I found in my experience was that I had to, like I say, I had to start thinking horizontally. There's an interesting kind of trade-off between these two that I found as well, is that the more homogenized the data from the back-end engineers, if they use similar technologies or they export their data in similar ways, that makes your life a lot easier, but it makes their life potentially more difficult. They don't want to all use the same technology. They don't want to all export the data in the same way or at the same time because they're independent teams and that's their priority. I think that's kind of something worth bearing in mind, especially when sometimes your back-end engineers and your data engineers might actually be the same people because your company's not that large yet and you're having to deal with these problems in a kind of smaller space. And so if you are one of those engineers who has to do a bit of data engineering and a bit of back-end engineering, I think it's worth bearing in mind that they're kind of different hats almost, that you have to think about the problems of your company in a slightly different way in order to achieve both goals separately. So, once I've started thinking horizontally and I understand a little bit about where my team sits into the wider picture of the team, I'm going to talk a little bit about something significantly more detailed and then something mediumly detailed and then kind of try and piece it all together from my experience. So, automated testing in the data sphere, I feel like is quite a young element. It's not quite as good as it was in my back-end engineering experience in most of the companies and people I've talked to. And I think that's because it is harder and it is different. the usual principles of handling back-end engineering testing and code cleanliness are based off writing a lot of unit tests, refactoring off the basis of those unit tests, and as such you can move quickly and in an agile manner in your team. Whereas with data engineering, it's quite hard to classify where exactly in a data pipeline that you've created are you going to test? Where do the tests exactly lie? So here is a generic data pipeline in which you get some data off a source, say a back-end engineer or a third party, and you've got it into your sphere, the things you own. You've got some files. You take those files and you're going to read them into some sort of framework. You're going to have an internal model for what a given row in that file represents. You're going to do some transformations, some joins, some groups, some aggregations. You're going to turn them into some output models. Those models will be written to files, and those files will be surfaced somehow to users. Now, given this kind of high-level structure, this tends to be how I think about every pipeline that I might build. This is a kind of single unit of data engineering work in terms of how I think about it. The thing at the top is actually really difficult to test or to deal with, because you're talking to a third party, it's a dependency you don't control, you don't know what data they're going to give you, they might mess it up and give you data in a format they said they wouldn't, etc., etc. So it tends to be done asynchronously, and I don't want to focus on testing it. Given that I'm not going to focus on testing it, I want to do as little transformations at that point in the pipeline as possible. I want to use whatever schema they give us. I'm not going to change it, I'm not going to rename anything, because I can't test it. It's a really difficult part to test. So my input file is going to be in the schema that I was given, and ideally in a structured data type, so not a CSV, so that I know what the types of each row of my data is. From here, this is the most important part that I've learned in the process. I tend to use Spark as my primary tool of choice, which is a fairly hefty framework and allows you to utilize the kind of breadth of Scala to do your testing. In that, instead of dealing with the kind of whole process of reading some files, transferring it into models, doing some transformations, turning it back, writing out the files, that's quite a kind of long and extensive test. It's quite difficult to do. So I focus on unit tests that can be done at this level. One of the most important things about this is that the declaration of the data going into your unit test can be adjacent to calling the functions which will do the transformations. And therefore, you can create a test which is very easy both to read and to write. And you know exactly what a piece of functionality of a transformation is meant to do. That makes sense? I realized that I was a little bit, okay, good. You're all nodding. That sounds good. Okay, so I focus a lot on these sorts of unit tests. Each function, any join I do, anytime I rename a column, anytime I want to do a group by or an aggregation, I'll write a unit test of that individual function. The slightly bigger level is that I also obviously want to check that I can read files in the format I expect them to be, and I can write files in the format I expect them to be. So I'll write a few integration tests at this level, but they're not as valuable, they're more brittle. The data is defined in a file rather than defined in the actual kind of unit test code itself. So I write a few of those as they are less valuable. However, there's a third thing I've sort of missed out, which is what I'm going to come to next. So it seems kind of obvious, but write unit tests. They're still really valuable, they're still really important. Kind of almost nothing's changed except the way you write them. However, there's a kind of third element to doing the technical data engineering work, which is that you've done your kind of small piece of work in which you think you know what data you're getting in, you think you know what data you're going to get out, then you have to actually run it with some real data. And as anyone who's done this type of work will understand, that's when things go wrong in all sorts of ways you could have never imagined, in which their strings were actually numbers, and they were lying about it before. So actually running things on real data. When using something like Spark, there's a couple of things in which this level of the process might be trying to check or trying to test. Performance is definitely a big part of this level of checking. You don't know how much data you're going to get in, how fast it's going to have to be. If you're using a tool like Spark, there's a lot of tweaks you might need to do to configuration to try and parallelize it and get it all running really quickly. And there's also a kind of loose correctness checking. You're not going to check every single row of your 1 billion royalties that you get every month, but you're going to get some idea of what you expect the output to be. And so you'd do some kind of top-level checks of, is it more or less correct? Is the schema what I expect? But when doing these sorts of tests, one of the things I find really, really important to get being effective is to make sure I'm testing very isolated changes. In that, if I'm going to run my pipeline on a cluster and I want to check the performance, I'm only ever going to tweak one configuration, one small change of code, and I kick off a cluster running it. This means that I end up creating a sort of table of every test I've run, exactly what I've changed, if the rows changed, and what the performance was. And that way you can be very, very methodical. And I tend to think of it like I'm a scientist who's being really meticulous with their checking that exactly what they've done has definitely improved the code that you're testing. With isolated changes, I fervently check the results. And that's kind of what I mean by creating a table of exactly what you've done. These sorts of tests can often take quite a long time. And if I want to check one thing at a time, that can be really time consuming. However, even with if I have like an 8-hour long process, which I want to test 15 different changes, because clusters are generally cheap, hopefully, and hopefully your changes are small enough that you can maybe break it down. So an 8-hour change, you can break it down to a 2-hour change, and then you could run 15 in parallel, and then you know exactly which configurations you need to change, and you kind of eliminate them. It's kind of like natural selection of the changes that you're going to do in your config. So performance tests like a scientist. That's how I think about that kind of section of the work. The way I see these three connecting is kind of essentially chronological. That's the order of work in which it tends to happen. I'm thinking horizontally, I'm talking to other teams, I'm getting my data organized. I then go really small, I think about the models, I write unit tests, I get my code ready, and then I move into a third stage of my working, where I'm actually running it, and they take a little bit longer. And they're very different ways of thinking within a given day of a data engineer. At least that's been my experience. Any questions at this point? Cool. So the fourth thing I do want to talk about is not cool quality, but code quality. Excellent. Cool quality. Right. Code quality. Just pretend it says that. It says code quality at the top. That's good. So I found that maintaining data engineering code is similarly quite difficult, especially if quite a lot of your code, if your declaration of transformation is done within a SQL sort of context, because it's very difficult to create arbitrary test data in SQL. So applying your transformations and creating your test data is very difficult to put in the same place. And so if you can find a way to bring those two together, that's really beneficial. And so in order to improve your code quality, the same principles for backend engineering apply, in that you need to have good unit testing, you need to have good regression testing, so that when you refactor your code, you are sure that you haven't broken anything and everything's still working as it was meant to. So you need to get the unit testing right in order to get the code quality right. But there's a kind of another caveat, which is that in that third stage I was talking about, where you're doing your longer term performance testing, the process has become quite long, in which you did your first 2 days, you wrote a load of unit tests, and now you're doing this longer day with lots of experimentation, which can take a few days to really get your pipeline speed down, for example. But you have to have the discipline after you've done that to still go back and refactor, because you will have changed some stuff, you'll have changed your code. And so it's a red-green refactor cycle from backend engineering, but just on a longer time scale. And you need to remember that even though you've got the performance down, it's definitely correct data, you still need to go back and do the refactor stage of your red-green cycle. I also tend to find that the code becomes really comment-heavy. I think this is because a lot of data engineering stuff requires a why as well as a what within the code. So you have to explain why you're aggregating these two things, or why these two products are the same. Hoovers and vacuums are the same, but in the context of royalty generation, two things of a similar name actually are the same. You need a comment to explain it. And so the usual concept that comments are bad and good function names are good doesn't quite work in a data engineering context from my experience. I think quite a lot of comments can be really helpful for explaining why your data pipeline works the way it does. And finally, it is achievable. You really can write clean, nice data code, which, yeah, I think it's hopeful, it's good, it's possible. So, in summary, when becoming a data engineer, I found I had to think horizontally, I had to think about the breadth of the company, not a kind of narrow responsibility. Write lots of unit tests, make sure you're using a framework and your functionality is available so that you can write lots of unit tests. They will aid you when you're caring about code quality towards the end. And when you're performance testing, make sure you're meticulous. You think like a scientist. You change one thing at a time, because you never want to have run an 8-hour test, but you actually changed 2 things and one of them broke it, and you have to go back. It's just, you don't want to do it.